True. In 1948, a young physicist sat in a lecture hall and watched some of the smartest people alive completely fail to solve a math problem. Not a hard problem, an impossible one. True. The equations for how particles interact were so tangled that even geniuses were getting different wrong answers, depending on which page they started calculating from. And then this one guy stood up and said something that sounded almost insulting to physics itself. He said, "Stop doing the math. Just draw a picture instead." Everyone laughed. True. 6 years later, he won the Nobel Prize. And today, every single physicist on Earth, from PhD students to people working at CERN, smashing particles together at nearly the speed of light, uses his doodles instead of the original equations. This is the story of Richard Feynman and the cartoon that broke quantum physics wide open. And by the end of this video, you will actually be able to read one of these diagrams yourself, which is something most people never learn, even if they took a physics class in college. So here is the problem physicists were facing before this trick existed. When two particles interact, say two electrons pushing away from each other, you would think the math is simple. Two objects, one force, done. But quantum physics does not work that way. In the quantum world, when two electrons repel each other, they do it by secretly tossing an invisible particle of light back and forth between them, like two people on ice skates, pushing a bowling ball between each other and drifting apart. Already strange, but here is where it gets worse. That tossed particle of light can, for a fraction of an instant, split into a particle and an antiparticle, which then recombine back into light, before continuing on its way. And that split and recombine can itself contain another split inside it, and another inside that one. Infinite tiny detours, each one mathematically possible, each one adding a tiny correction to the final answer. To calculate the true behavior of two electrons repelling each other, you technically need to add up every single one of these detours, all the way to infinity, using an equation so long it would not fit on this screen. Physicists before Feynman were trying to do this with pure algebra. Rows and rows of Greek letters, integrals stacked inside integrals, spread across chalkboards the length of a hallway. People were losing months to a single calculation. And even then, mistakes were everywhere because there was no visual way to keep track of what term represented what physical event. It was like trying to write a novel using only a list of individual letters. No words, no sentences, just raw symbols, and being expected to keep the plot straight in your head. So Feynman did something that at the time felt almost like cheating. He said, forget the algebra for a second. What if every one of these terms in the equation actually represents something happening in space and time? What if I draw it? He took a piece of paper and drew a horizontal line for time moving left to right. Then he drew a straight line for an electron coming in from the left. He drew a wiggly line for a photon of light. And he drew where they met as a simple dot called a vertex. That is genuinely almost the entire system. Straight lines for matter particles like electrons. Wiggly lines for force carrying particles like photons. Dots where lines meet, representing an interaction happening at that instant. That's it. That is the entire visual alphabet. And here is the part that made physicists in that lecture hall go quiet. Every single one of those infinite algebra terms, the ones that used to take a full chalkboard to write out, could now be drawn as one specific diagram. A straight electron line, a wiggly photon line, connecting to another straight electron line. That's the simplest interaction. One diagram, one equation term. Want the next level of correction, the one where the photon splits into a particle and antiparticle before recombining. Draw a little loop in the middle of the wiggly line. One tiny loop equals one specific mathematical term, and there are fixed rules for turning that loop into the correct piece of algebra. Suddenly what used to be an abstract, error-prone written equation became something you could literally see. A physicist could look at a Feynman diagram and instantly understand. This is an electron emitting a photon. This is a particle-antiparticle pair, briefly forming. This is two photons merging into a single particle. The picture was not just easier. It was doing something equations never could. It was showing you the actual story of what was physically happening between those particles, frame by frame, like a comic strip of reality itself. But here is where it gets genuinely mind-bending, and this is the part almost nobody outside physics knows. In a Feynman diagram, an antiparticle, the antimatter version of something like an electron, is drawn as the exact same line as a regular electron, except the arrow on it points backward in time. Not backward in space, backward in time. Feynman was essentially saying mathematically, an antiparticle behaves exactly like a normal particle traveling backward through time. Read that again. In these diagrams, when you see a positron, the antimatter twin of an electron, what you are actually looking at, mathematically, is an ordinary electron moving from the future into the past. This was not just a cute drawing trick. It reflected something genuinely strange and true about the deep symmetry of physics. That the equations governing particles do not care which direction time flows. And Feynman found a way to make that invisible truth visible on paper. People spent entire careers exploring the implications of that one arrow. And this is usually where most explanations of Feynman diagrams stop through, because most people think the picture itself is the whole trick. It is not even close. The real trick, the part that actually solved the crisis in physics, was what Feynman did next. He created a strict set of rules for turning any diagram directly into its correct mathematical formula. Every straight line, wiggly line, through, and vertex dot had an exact corresponding piece of algebra attached to it, almost like a lookup table. Draw the picture that shows the physical story you're interested in, then mechanically translate the shapes into equations using the rulebook, and multiply everything together. What used to require days of careful, error-prone derivation from first principles could now be done by, essentially, drawing the right doodle and following a formula sheet. A calculation that once took a brilliant physicist a week could now take an afternoon. And crucially, because the diagram represented an actual physical process, physicists could organize their calculations by asking a completely different kind of question. Instead of asking, what does the terrifying algebra say? They could ask, which physical processes matter most here, and only draw the diagrams for the important ones, ignoring the astronomically unlikely 50-loop detours that contribute almost nothing to the final answer. The picture was not just a translation tool, it became a filter for human intuition, letting physicists reason about probability and importance visually, instead of getting lost in a swamp of symbol. Single shift is arguably one of the most important quiet revolutions in 20th century physics, and most people have simply never heard of it because it happened on a chalkboard instead of in an explosion or a headline. Now here is where the story takes a turn that even physicists find almost funny in hindsight. When Feynman first showed these diagrams to his fellow physicists at a conference in the late 1940s, some of them thought it was borderline absurd. Julian Schwinger and Shinichiro Tomonaga, two brilliant physicists working on the exact same problem, had independently developed their own solutions using dense traditional mathematics. No pictures at all, just pure formal algebra, arguably more rigorous on paper. For a while in certain academic circles, Feynman's cartoon approach was seen as almost too simple to be taken seriously, like bringing a crayon drawing to a formal exam. But then something happened that silenced the doubters almost overnight. Physicists using Feynman's diagrams could solve problems faster, with fewer errors, and could actually see connections between calculations that were completely hidden in the pure algebra approach. Freeman Dyson, another physicist at the time, proved mathematically that Feynman's diagram method and the more formal Schwinger-Tomonaga method gave identical answers, meaning the cartoon was not a shortcut with hidden mistakes. It was a fully rigorous mathematical tool wearing a disguise as a simple picture. Once that was proven, the floodgates opened. Within a decade, the crayon drawing had completely replaced pages of formal algebra as the default working language of particle physics, and has stayed that way for over 70 years. In 1965, Feynman, Schwinger, and Tomonaga shared the Nobel Prize in Physics for their work solving this exact problem. But here is the detail that always gets left out. Feynman's diagrams did not just help him solve the problem. They became the permanent tool the entire field still uses today. Nobody draws Schwinger's formal derivations by hand anymore. Every single physics student learning particle physics right now, this year, in 2026, is taught to draw straight lines, wiggly lines, and vertex dots, exactly the way Feynman sketched them out on that chalkboard nearly 80 years ago. Let's slow down for a second, because I want you to actually be able to read one of these things, not just hear about them. Picture two straight lines coming in from the left side of the page, angled toward each other, representing two electrons approaching one another. Where they get close, instead of touching, a single wiggly line connects them, angling off diagonally, representing a photon being exchanged between the two electrons. Then the two straight lines continue out the right side of the page, now angled apart from each other. That is the entire diagram for two electrons, repelling each other through electromagnetic force, drawn using maybe 6 or 7 lines. And once you know the rulebook, that simple sketch translates directly into the exact mathematical probability of that interaction happening, calculated to a precision that has been tested and confirmed by real experiments to more decimal places than almost any prediction in the history of science. That's not an exaggeration. Quantum electrodynamics, the theory these diagrams describe, has been verified experimentally to an accuracy of about 1 part in a billion, making it one of the most precisely tested theories human beings have ever created. And the tool used to calculate those mind-bendingly precise predictions is, at its core, a picture made of straight lines, squiggles, and dots that you could sketch on a napkin. Today, Feynman diagrams are not just used for electrons and photons. Physicists at places like CERN use more complex versions of these same diagrams to to predict what happens when protons collide at nearly the speed of light, the exact kind of collisions that led to the discovery of the Higgs boson in 2012. Before that experiment ever happened, physicists had already drawn out the diagrams, predicting exactly what kind of particle debris pattern would appear if the Higgs boson was real. And when the actual experimental data came in years later, it matched the predicted diagrams astonishingly closely. A doodle Feynman sketched to save himself a headache in the 1940s helped scientists confirm the existence of one of the most fundamental particles in the universe over 60 years later. So the next time someone tells you that quantum physics is only understandable through impossibly advanced math, that regular people could never grasp, remember this. The actual working tool physicists use every single day in the most advanced particle physics labs on Earth is built on straight lines for matter, wiggly lines for force, dots where they meet, and one arrow that quietly points backward through time. Feynman did not simplify quantum physics by removing its complexity. He simplified it by finding the picture that was hiding inside the complexity all along. The story the equations were trying to tell the whole time, if only someone had thought to draw it. If this kind of explanation clicked for you, the kind that takes something that sounds impossible and actually makes it make sense, that is exactly what this channel is built around. Hit subscribe if you want more of this. Drop a comment telling me what confused you the most or what topic you want explained next, and I will see you in the next one.